thank you very much for that lengthy introduction. It gives half of my life. You don't know how much of a pleasure it is to speak to real people again. Instead of that little screen that I normally look at and for the last 2.5 years. The invitation to talk up here, I just accepted gladly, even though it was a long drive. Without further ado, I would like to indicate to you that we've got a lot of ground to cover here, because I'll talk about my path into nuclear, because I'm not a nuclear person as such. Talk about used CANDU fuel and what it actually is. Talk about a better reactor from our CANDU reactor. Recycling of used CANDU fuel, and then give you a time frame of how fast we can actually clear the radioactivity from our stored stockpiles that we've got now, the 60,000 tons, or I'll use an example of 15,000 tons. And then I'll take a leap and say, well, if you don't do this, Dryden, what are you going to do? And I'll give you some suggestions which are off the top of my head. Since we've got a lot of ground to cover, I want you to take home this as a message, okay? I calculated what it cost for a cube of sugar of that size that everybody knows. And Colleen actually got the price in Dryden, so it ranges here from 1.7 cents to 2.4 cents. If you get that same volume as gold, it would cost you about $3,000. If you take that same volume of used CANDU fuel, you can make $21,000 worth of electricity if you cycle it through fast neutron reactors. That's used CANDU fuel. You call it waste. So remember that, or if you don't like this scientific approach, look at this the next time you have a cup of coffee. That cube of sugar creates $21,000 worth of electricity. No, not the sugar, it's the equivalent used CANDU fuel. And we have almost 3 billion of such cubes. So you can see how much value there is in our used fuel. Now, I didn't start out that way. This is my beginning. So at the Ontario Cancer Institute just after 1958, and the people here, this is Harold Johns, who actually developed what was known then as a cobalt bomb, a cobalt irradiation unit. And here he's, with his physicists, he's in the process of putting a new cobalt source up into the head of this radiation machine. It's what physicists do. They don't deal with patients, they deal with the stuff behind the curtains. We sort of design machines. And instead of having just a single beam come down straight, we have a machine that rotates around like this, and that basically is focused on the tumor, because we want to kill cancer cells, and it spares the normal tissue around it, because the normal tissue around it gets less of a radiation dose. And we even tilt the device this way and that way. Now, more modern devices like this actually take it almost to the nth degree, where you have a cobalt source which gives you a ray that's coming out this way, and then you put a patient in the way, and that patient gets irradiated from this thing sort of swinging around to all directions, always focused on the tumor. So the tumor gets the largest radiation dose and gets killed. And so this is sort of the equivalent of about 100 such rays, all focused on somewhere inside the head where a tumor was discovered. Now, it takes time for that thing to whip around and irradiate a person. So we engineers say, well, there's a quicker way, and that is to use multiple sources, 200 in this case of cobalt-60, in a lead cast, which has holes which are all focused on one spot. And so you can rotate this and shut the thing off and put the patient inside the device, rotate it so it actually focuses on the tumor, and within a few minutes you can take the patient out and he or she can go home. So my work then was involved, in a sense, with gamma rays, which cobalt produces. They're fairly high energy gamma rays. And we, of course, want to shield ourselves from that, and we can do that quite nicely with lead or tungsten or even enough concrete. All you need is mass in the way between you and the source. So we know how to shield ourselves. I also worked with other biological isotopes, which are tracers of biochemical reactions, biological reactions inside. And of course, they have to mimic natural things that happen inside the cell. We all have hydrogen within us, so tritium is a substitute for that we can trace, or carbon-14, because we're carbon units anyway. Sulfur is in proteins, phosphorus is in DNA, and potassium is in different organelles inside the cells, so they're all useful. Now those basically are beta rays, and you can stop those with rubber gloves, or if they're high energy, 1 centimeter of perspex, acrylic, that plastic transparent sheet will do to protect you. So we know how to protect ourselves from radiation. I should explain alpha, betas, and gammas. They're actually unknowns. When they were discovered, the scientists didn't know what to call them. And if you have an unknown, normally you call it X. But X-rays had been discovered shortly before that, and so you couldn't use X. So what do you use? A, B, C? That doesn't sound scientific enough. So you become Greek, and you go alpha, beta, gamma. Okay, so just because they're unknown, you give them those highfalutin names, and they've stuck. So now everybody's afraid of alpha, beta, and gamma rays, but they're ABC things, okay? And then we found out that alpha rays are actually the same as the atoms of helium, the nuclei of helium atoms. So when they slow down, then they become normal helium, and you use it to blow up your kids' balloons. Beta rays are the same as electrons, and gamma rays are just like X-rays. Sometimes they're less energetic than X-rays, more often they're more. Okay, so that's alpha, beta, and gamma. Now, I used uranium as well, so that was my introduction to uranium, but I used it as an electron microscopist because it acts as a stain, a dye in the electron microscopes. And alpha rays are actually stopped by a piece of paper, even though they're very energetic. So obviously, we know, like I said, how to protect ourselves. And it's not necessarily hard. There's nothing easier than to detect radiation. And then when I retired, I said, well, what actually happens to the radioactive leftovers? Because while they decay away with 12.5 years, that's longer than the life of a graduate student in college. 14 days, they'll decay away just quickly. But then you have 1 million years and so forth, 1 billion years for uranium. And so what happens? And so I asked around, because the epitome of nuclear isotopes, waste in a sense, is what comes out of a nuclear reactor. And you saw that thing come out right there. And I asked our former graduate students who were working for AECL, now CanLab, up in Chalk River, or Ontario Hydro, and they said, well, talk to the Nuclear Waste Management Organization, because they're sort of charged with doing things to protect us. And they essentially said, well, what we want to do is build a deep geological repository. Here I've put it between Ignace and Dryden, where you're talking about, and they want to put those used CANDU fuel bundles with a radioactivity in them down into that repository. And I was perfectly happy with that answer. Because that same idea had been around since 1977, when Professor Hare did a 3-month study and said, well, the best place to put it is in the formation of igneous origin in the Precambrian rocks, better still into plutons with no fractures and low in quartz and high in feldspar. Quartz doesn't absorb things if things leak, but feldspar seems to. or shaly rocks in southern Ontario or in the deep ocean. So that was in 1977. And then things were studied. We built a deep underground research laboratory in Pinawa, Manitoba, in the, I'll get the name of that pluton out there. Basically the seaborne panel said, well, technically it seems to be demonstrated that it's safe, but you really haven't convinced anybody in the public. And so that was the task really of the Nuclear Waste Management Organization, which was established in 2002. And they had a final study, of which I actually have a copy here because my name ended up in it as well. And they decided on an adaptive phased management, which was agreed to by Parliament. And they went about to select a site with public support. And we're still doing that. And I was happy with that until my wife and I took a trip to Newfoundland and went to the fjord there at the Western Brook Pond. And I looked up there, and there were these, this mountain that had been extruded out of the earth, and then the gap was put in by glaciers and so forth, and it was cracked all over the place. And you say, well, it's probably just surface things. Well, that's 700 meters high. So imagine that being down in the ground. So I said, well, you know, is there any evidence that this is reasonable to do? And, you know, scientists make measurements all over the place, including underground. And here at the Con Mine in Yellowknife, which is also in the Canadian Shield, they found that the mean transit time of rainwater down to this level of the drift tunnel at below 1 kilometer was about 17 to 23 years. And even in the underground laboratory in Pinawa, in the Lac du Bonnet Pluton, which is like your Revel Pluton here, I presume. I don't know if it's the same rock structure, but they actually made measurements inside, say, a hypothetical cube like this. Mark Jensen drilled boreholes, 12 of them, and then sealed off sections of the boreholes and measured the flow of water from one borehole to the next. And since it's through solid rock, supposedly it should take forever. Well, it didn't. It took 7 days for the tracers to move with water from one borehole to the next, and then about 25 meters apart. So I thought, gee, you know, that doesn't sound very good because, you know, if you calculate that's about 1,000 meters or 1 kilometer in a year, or in the Yukon mine, about 1 kilometer in 15 years. And the NWMO says we've got to protect ourselves for the order of 1 million years. That's a lot. And so I said, are there any strata which are denser than that? And sure enough, people had made measurements, this time in the deep ocean. You know, from a depth of 300 meters down to 1,200 meters, they measured something called the permeability. It's the ability for water to penetrate, which was 10 to the minus 17 meters squared. Well, I don't know what that means. You don't either. But if one takes the same number for the Con Mine, it's up here. And the difference here is that this is relatively fast, and this is about 1 billion times slower. So I figured, oh, we got to go into the deep ocean. And the Japanese and everybody else, oil company, drill into the deep ocean quite nicely. So the idea then is to take, in this case, a drill ship which uses a riser technology, which is a tube from the drill ship to the bottom, so nothing gets out into the ocean. And they drill down into the ground, and then the idea would be to take our waste canister and seal them in the borehole. The technology is there. And we even have nice, shallow, accessible areas in our ocean which move, because the ocean plates move and end up going underneath the continent. And so we have the Cascadia subduction zone, which is right off Vancouver Island, right there. And the ocean floor moves at about 5 centimeters per year underneath Vancouver Island. So I figured, well, the idea then would be to, if I take a crosscut here, to take that ship and have it drill a borehole right at the edge of that subduction zone, fill that borehole up with nuclear waste, and then have nature take its course, and it will move along at 5 centimeters per year underneath the North American continent, and by the time it reaches the middle of Vancouver Island, it's about 40 kilometers deep. I figured that was safe. And so I said, well, what's it cost? It's possible, but one borehole, for instance, 2 feet in diameter, 1 kilometer length, that's 2 feet in diameter was the biggest drill bit I could find on Earth in Australia someplace. And said, what would it cost to that drill ship? And they came back and said it would take 30 days to drill 1 kilometer deep, and it would cost about $21 million. Well, that's bigger than my research grant at university. So I said, well, how much of the nuclear waste will it take? Well, the volume of that borehole is about 660 cubic meters, and the annual volume of used fuel in Canada is about 290 cubic meters. And so it would fill this borehole up to less than half, and that leaves the rest of it for cladding and containers and sealing and capping and so forth. But I still thought it was expensive. And so I wondered whether one could be more efficient. And I said, is this material really waste, or is just a smaller portion waste? And so I did what I should have done in the first place, is to find out what nuclear waste is. And fresh uranium fuel that is put into the reactor is pure uranium, which actually comes in 2 types of atoms. One is U-238, which is over 99%, and U-235, which is less than 1%. And this is usually considered the fuel in nuclear reactors, this U-235 in blue. It's called fissile because it splits easily. And so this fuel bundle is put into the reactor, and about 1 year later it comes out the other side and is now changed. A lot of the U-235, which was considered fuel, is gone, more than half of it. It's created energy. And some of the U-238 has been converted into other atoms, plutonium of 239, 240, 241, and you notice some of them are blue, which means that they can also be easily split. And so we actually get 50% of the energy in the reactor from this U-235, and the other 50% from these so-called transuranics, which come from U-238, are changed in the reactor. And the product is called fission products, in other words, split atoms. Now, what do all these things mean anyway? And I apologize for people that never liked chemistry. But you probably had a chart like this in your chemistry class on the wall. And the smallest atom on Earth is hydrogen, and then there's a whole bunch of them, carbon and so on and so forth. And the largest atom on Earth, naturally occurring atom, is uranium. But there are others here. And there's this whole row of atoms. Plutonium is in there, for instance. All of these are called actinides in this row because they start with actinium. And the ones that are bigger than uranium are called transuranic actinides. In other words, they're on the other side of uranium from the normal atoms. What are fission products? Well, if you split uranium exactly in half to get the energy out, then the atomic number 92 becomes 46, and 46 is palladium. So you get 2 atoms of palladium. So you might say this is so-called waste, but it's palladium. But because I don't know how good you are with your axe when chopping wood, you don't exactly chop in the middle most of the time. At least I don't. And neither does this little axe called a neutron, which splits the uranium. And so there's always sort of a smaller half and a bigger half, and a smaller half and a bigger half. And if, for instance, if we take Superman's atom here of krypton at 36 in atomic number, its partner is 56, which is barium, because the two of them together add up to uranium. So all of these fission products sort of come in pairs. Even palladium comes in twos if uranium is split that way. So there's no mystery about any of this. It's just normal chemistry, normal elements. And the marvelous thing is that since 1970, splitting these 60,000 tons of uranium, or at least part of it, has created 4.4 terawatt hours of electricity. I don't know how big that is. But we've paid $440 billion worth of electricity since that time. And what does that mean? Well, if I divide by the population of Ontario, that's $30,000 for every man, woman, and child in Ontario. That's come from nuclear energy in terms of electricity. And all of that has created or avoided the emission of a whole lot of carbon dioxide if you had used coal to create this electricity. This many billion tons of it. You know, these are astronomical numbers to me. And all of that has come only from less than 1% of the uranium fuel that we have in the fuel bundle. I mean, that's amazing. But it means also that basically we've got 99.26% of the uranium that is not consumed. And all of that could create energy. But what we want to do is just throw it away. I mean, this doesn't make sense. We do it for the CANDO fuel bundle, but let me give you an example that's closer to home. Here I have a birch log, which I put in the fireplace, okay? And I light the fire because, you know, birch bark is very flammable. It's easy to light. It's like kindling. I mean, you can light a fire in the bush in the rain with birch bark. It's neat. And when it comes out, if you don't do it right, it looks like this. It's charred, the birch bark is burned off, and we don't throw this away like this, which is what we want to do with the used CANDO fuel bundle. Here's an example, just in case I didn't have the bun. And I should thank Colleen for those birch logs. I didn't bring them along on the airplane. But here, if you have the birch bark, it's made of hardwood and birch bark. If you put it in the fireplace, it looks like this. It's obviously not a good fire to build like this, but if you light it, then it flames up and the birch bark dies, and you've got your charred log with the heartwood still left, some bark, some char because some of the heartwood is attacked, and tar, which you don't want to lick because it might be carcinogenic, and some ash. Well, you've got exactly the same thing in the fuel bundle. Most of it is still U-238, which is like in the hardwood. Some of the bark, the U-235, has been burned. So you've created some transuranic actinides, those heavier atoms, which is like the char and the tar, because they also are radioactive for a long, long time. And you've got fission products, which are perfectly good. I mean, ash, potash, you can use as fertilizer, or my grandmother made soap out of it. So it's useful. And so the fission products are also perfectly good atoms. And so the idea is to build a better fire, build a better furnace, or build a better reactor. The CANDO can't do it, and the payoff for this would be that the 99.26% of heavy atoms that I've got left, if you split them, would give you 134 times more energy. Where does that number come from? Well, if you divide 99% by this, you get 134 times. That's a lot of energy that we're trying to throw away as waste. It's in numbers astronomical. Again, $60 trillion worth of potential electricity there. And again, if I use this example here, that's equivalent to $4 million worth of electricity per man, woman, and child in Ontario. That's a lot of money. And the amount of carbon dioxide that we avoid putting into the atmosphere is so big that it actually ends up being 16% of all the carbon dioxide in the atmosphere of the whole Earth. That's what this thing is worth. So how do we do it? Well, I decided to build a better CANDU reactor. And you can do that if you have a little bit of mathematics. It's not very hard. And you can do it on a laptop because a laptop doesn't blow up, it doesn't melt. And so if you do something wrong, well, it's too bad, you just try again. And I did, and I had this eureka moment where the new reactor worked, and I went to now my newfound friends in nuclear energy, and they said, Peter, why don't you read the literature in the 1950s and 60s? And it turns out that it had all been done. The My Better CANDU reactor turns out to be a fast spectrum reactor. It uses fast neutrons instead of slow neutrons. And they maintain the kindling, and with recycling, they can essentially use all of the fuel and replenish the fuel after cycling with just U-238, which is the hardwood. And so those are sort of ideal. And what I was remarking after reading the literature is that countries had used these kinds of reactors for ages. The very first one ever to produce electricity by nuclear power was in the US, called the EBR-1 in 1951. So this is almost older than I am, but not quite. And its bigger brother, the EBR-2, actually had 20% burn-up, whereas in the CANDU we have less than 1% burn-up. And they even recycled 5 core folds at 20%, so that's one whole reactor full of uranium recycled and used to create energy. And the most modern such reactor is in Russia. It was put into operation in 2016. And just 2 weeks ago, they announced that they had actually fueled this reactor fully for the first time now with recycled used reactor fuel. And they have a facility, a recycling facility, automated, because they're dealing with radioactive stuff. So you want to stay away from it, but a machine doesn't care. And recycle that irradiated fuel. They call it irradiated fuel. It's the used fuel. Instead of storing it. So we're heading in that direction. You may not know it, but the small modular reactors that you might have heard of in the newspapers that Canada is looking at actually is a whole series of reactors, these 5 here and then about 100 more. And 3 of these that I've indicated here are of this fast spectrum type of reactor. They come in different sizes, and I'm happy to say that New Brunswick Power is actually chosen to look at this one, which is 100 megawatts, and I'm trying to help them to also get into fuel recycling. So I say recycling the fuel to extract the fission products. That's the ideal, because all you have to do is take the fission products out and the rest should work again. But we're not quite there yet. We actually, the chemistry that we've got divides it into 3 fractions. We can readily do pure uranium, which is the largest part. We can get pure fission products out, but there's some uranium and some fission products left in this mix of all of the transuranics. But the transuranics, remember those blue plutonium-239 and 241, they're ideal for starting these small modular reactors because they're just like U-235. Now, the usual answer you get is, oh, but it's expensive. Well, that's sort of emotional. You should ask, how expensive is it? And so we did a study in the 4th year course at the University of Toronto in chemical engineering, and those students were asked to look at 3 different technologies: Purex, which is developed by the military really to produce pure plutonium-239 for bombs. Militaries do that sort of thing. Electrorefining, which is also called pyroprocessing because it's done in molten salt, and fluoride volatility. Now, all of these techniques are used at least partially by Cameco, for instance, Purex and fluoride volatility to purify their uranium, and Alcan uses it not for uranium, but for aluminum, obviously. And these students, because they had to get a degree or wouldn't, they had to pass the course and they were examined by experts in the field, came up with numbers that were 7,000 and 1,300 and so forth, and they're close to 1,000 for the 3 technologies. And it's per fuel bundle because, if I give you millions of dollars here, then it becomes meaningless yet. But per fuel bundle, one can understand these numbers. And you say, well, but these are students. Let's get some experts in the field to do it. And if you look hard enough, you can find numbers like 8,400, which is $1,000 different, $300 difference here, and the order of $50 difference there, from experts at Argonne National Labs in the States, and also the University of New Brunswick. Some staff members had done the calculation there. Now, how does it compare to anything? Well, the relevant number, I think, is what it costs to put a fuel bundle down into a deep geological repository. And that number is $3,600 per fuel bundle. Now, where's that number come from? Basically, you and I have been contributing to this fund from our electricity bills to take care of the costs. And somebody asked a question earlier today, where's the money come from? And at that time that I made this calculation, we had the order of 2.8 million fuel bundles, used fuel bundles, that we contributed to in that number. Now, in the meantime, this has gone up to over 3 million, and that's gone up to about 11 billion, but the ratio is still roughly the same. And so you can say, yes, recycling is more expensive than burying it if you use that particular technology, but it's cheaper if you use by a factor of 3 if you use the other technologies. So it depends on what you choose. And like I said, this material is good for starting fuel for these small modular reactors. And why is that important? Because all of these small modular reactors require enriched starting fuel, enriched in U-235, in this fissile material, in the kindling. Otherwise, they don't start, because they're so small, they lose a lot of neutrons that come out and so forth. And Canada has no enrichment facility because we decided politically to do that way because we didn't want to build bombs. And that technology basically goes in the direction of building bombs. And so the USA also, I was surprised by this, has no highly enriched uranium for civilian use. The military has it. And so the US must purchase it from Russia or China or France, and you know the political implications of that nowadays. And so basically, it would be good to go in this direction, doing it ourselves from the transuranics of our used fuel. Now, if we did buy U-235 at 20%, for instance, which is required for the ARC 100 or PRISM reactors that I mentioned before, it would cost $152 million to start to furnish the fuel for this one reactor. Now, if you went the other way and created starting fuel from the transuranics, each would cost $1,300 per fuel bundle, and you needed almost 50,000 fuel bundles. But even that large number is $62 million, which is less than half of the cost of purchasing it from a foreign power. So it gives us indigenous reasons. And there's another wonderful side effect that we have, which is the elimination of the million-year radiotoxicity. You'll say, how does that work? Well, remember this gentleman that was handling these fuel bundles with his gloves? The gloves are actually there to protect the fuel bundle from the sweat in his hands, because sweat has carbon in it, and you don't want the carbon to go into the reactor and become carbon-14. And so he's protecting the reactor, you might say, not himself, because the uranium alpha particles just can't get out of that fuel bundle sheath. You can see the little sheath out in the hallway. But once it's in the reactor and comes back out, it's about 1,000,000 times more radioactive. But radioactivity decays away. And so since I have, I should mention that this is a factor of 10 each time. So there's 10, 100, 1,000, 10,000, 100,000, and 1,000,000, just to get it all on the same scale. And similarly, time here is 1 year, 10 years, 100 years, and so forth. 1,000,000 years is right there. Okay, so the radioactivity decays away with time, and I've divided into those three fractions. One is the fission products, which decay, well, they're really very highly radioactive to start with, but they decay relatively quickly, so that even after 1 month, they're down by a factor of 100, and after 10 years, they're down by a factor of 1,000 in terms of radioactivity. And the oldest Pickering fuel that we have that came out of the reactor somewhere in 1971, its fuel is now at roughly this stage, where the fission product radioactivity is lower than the ones of the transuranic actinides, those plutoniums and so forth. And they now will stay there forever, basically, until close to $1 million years. That's where the million-year problem comes from. Okay, but remember that these transuranics, these ones here, are excellent starting fuels in all small modular reactors. So we extract them from our used fuel stockpiles and put them into SMRs, and they start those reactors and get burned. And so what happens is that as we do that, those transuranics in our stockpiles are gone. And what you've got left is the fission products and the uranium that was there. Well, uranium won't decay until about another 4 billion years. So it'll stay that way, fairly constant, just about forever. And it's not very radioactive at all. And remember, you can shield yourself from it with a sheet of paper. So this recovered uranium actually is good replenishment fuel in these types of reactors, which are the fast neutron reactors, which are also small reactors. And so we can even use the recovered uranium and create energy from it, and so that goes away. And so what we've got left with is essentially the fission products. And even in the oldest Pickering fuel, we've just got two major radioactive isotopes, strontium-90 and cesium-137, and they will decay eventually as well. But in the meantime, we'll find out that they're actually useful, because what do we do with these fission products? Do we put them into a deep geological repository? Well, remember, even at this point, most of them are non-radioactive. That's all of these here. Oh, this is an indication of the mass of the different fission products at different atomic numbers. And I've given the names here from gallium, silver, cerium, europium, and so forth, and everything in between. Perfectly normal atoms, and now non-radioactive after a certain length of time. The only ones that are radioactive are the strontium here and the cesium up there. Whereas, even right away, once you take the stuff out of the reactor, 3 of them here are essentially non-radioactive, and they're rather valuable because palladium, rhodium are catalysts, chemical catalysts, and you use them in your catalytic converters in your cars. So they're useful right away, but of course, if we wait 50 years, we can use all of the rest of them as well. And even the strontium and the cesium are useful in their radioactive state as gamma sources, as measuring devices. You probably saw even the irradiation unit that I had on my first slide, where the little lady was sitting there with this strange-looking thing against her chin that had cesium-137 as a gamma source. And the strontium-90 emits electrons, and so it is being considered as a 30-year battery, a long-lasting battery, useful in Arctic situations or even space and so forth. So even those are useful fission products. Altogether, all the fission products in 50,000 tons of fission products would fetch about $150 billion or $3 million per ton. Okay, just to give you an idea of that. So how fast can we do this? If we consider the time frame, it depends, of course, on the number or size of the fast spectrum reactors that we want to make starting fuel for. And also on the size of the recycling facility. They sort of have to be matched so that you don't make one too big and the other too small. If we take a particular example that's hot at the moment, Pickering is going to close down in 2025, the Pickering reactors. And they have a power of about 3,000 megawatts. They supply a lot of electricity. And in the meantime, over the years, they've collected 15,000 tons of used CANDU fuel. Now, if you look at in terms of fractions, that's 14,840 tons of uranium, recoverable uranium, 110 tons of fission products, and 60 tons of these mixed transuranics of plutonium and neptunium and americium and so forth. So what do we do with them? Well, if we now consider a fast spectrum reactor like the PRISM reactor, which is 300 megawatts, and take 12 of them, so we have a total of 3,600 megawatts that replaces Pickering and basically also replaces the two reactors which were shut down a few years ago. Now, each of them requires 5 tons of fissile material from the transuranics. And so altogether, they require 60 tons of mixed transuranics and some recoverable unit. Where are we going to get 60 tons of that mixed transuranics? Well, right there. Okay, so that basically we can take all of the long-lived radiotoxic transuranics from the Pickering fuel, the used fuel, and put them into these reactors to keep Pickering, or the equivalent, running to give us more electricity. So it essentially eliminates all of the long-lived transuranics from the Pickering stockpile, right there, with 12 reactors. So how long does it take? Well, how long does it take to build 12 reactors? Not very long, a few decades. So what about the rest of it? We've got this recovered uranium. Well, in a sense, it's non-radioactive, so we can just leave it, you might say, on the lab bench. I had two kilograms of uranium on my shelf in the lab for 34 years. And nobody really worried about it. They just told me not to put it into the refrigerator with the sandwiches that I have for lunch, because the only danger there is that you ingest it. So it's this recovered uranium is effectively non-radioactive. But even so, at each fuel cycle, because these prisms, these reactors produce fission products, and the fission products gobble up neutrons, so eventually the reactor has to be refueled, get the fission products out, and replace the fission products with uranium, U-238 is all they need. How much? They need about half a ton of uranium per reactor per year, or these 12 take 6 tons per year. And so where do we get them? Well, from right there. We've got 14,800 tons right there, so the arrow should go the other way. We use that material there. How long does that last if this is per year? Well, divide one by the other and you get close to 2,500 years. And remember, you don't have to store this safely in a DGR, because I can have it on my lab bench if it were smaller quantities, okay? So that basically takes care of the used fuel story, except it doesn't take care of Dryden, which is looking at a deep geological repository and obviously the monies that are involved with that. And so I thought, well, what would I do if I lived in Dryden? Well, I tried to persuade the mayor of Ignace about 12 years ago that he should get a small modular reactor and go in this direction rather than a deep geological repository. And I'm pleased to say that even though he's retired, he's in the audience here today. I met him again after 12 years. So I thank you for coming. Effectively, I said, get a fast, small modular reactor for the region and recycle the used CANDU fuel locally. That gives you jobs, it gives you activities for not just a few decades to dig a hole, but forever, just about. And if you've got excess, you can sell the electricity, and it's, in a sense, even better than that. The monies already exist because we've got the $11 billion for a deep geological repository, which we could redirect in this direction. And the Nuclear Waste Management Organization can actually do the recycling, because as a federal organization, they can't do energy, but they can recycle. And the Nuclear Fuel Waste Act, which created them, actually has paragraphs in it which sort of foresaw something better happening perhaps sometime in the future. So it's possible to change for the NWMO. So tell them out there to change and go in this direction. Okay? So if we look at Dryden, for instance, it has a population of about 7,400. Maybe you can correct me. Each person requires about 3 kilowatts of electricity to keep them warm, to keep their tea kettles going constantly all year. So that's three tea kettles worth per person. And that basically would require a reactor of 22,000 megawatts to do that. Well, those reactors exist. If Ignace did it all by itself, it requires a smaller reactor, about 4,000 megawatts, and that exists as well. If you include Dryden, Ignace, Lake Wabagon, Sioux Lookout, and so forth, and Kenora, then you require something the size of the ARC 100, close to 100 megawatts, and so forth. But nuclear is created from heat. And when you do that, you throw about 2/3 of the energy as heat away. And you can use that heat to heat your houses. It's non-radioactive, okay? Even though in the reactor itself, but you can have transfers which then basically have barriers in between. So it's non-radioactive heat. They do it in Europe, and their range is the order of 50 kilometers. And if you have it in Dryden, then you can reach Kenora on the one hand and Ignace on the other, and heat their houses in the winter and have excess electricity to sell. If you want to include Thunder Bay, then you can't reach the heat anymore, but you can get a prism reactor, and that would include Thunder Bay as well in this group. So I would say go in that direction. Is it a big job? Well, for instance, an electro refiner, as I was saying in this pyroprocessing process, one of this size uses about 10 tons in a year, say. 250 days is less than a year. And you see how small or big it is. And the requirement for a prism reactor, which would take care of the whole region, is 3 tons per year. So really, this is almost excess. Unless you use the used CANDU fuel to start with, you need a little bit more. And how big is that if you have the entire facility to go from used fuel to new fuel? It's this big, where this device here is that little pot there. So it's one big barn full of stuff. So it's not enormous. So in summary then, we've got 60,000 tons right now. 59,000 tons of that is just plain, normal, non-radioactive, in quotes, uranium. It's radioactive, but its half-life is 4.5 billion years. So it's very little radioactive. It's got 300 tons of transuranics, which is the long-lived radioactive, radiotoxic stuff, and that is good for starting these reactors. You can do it for all of Canada because we're going in that direction. We have to, and I can explain that too. And then we've got these fission products, which are the small, short-lived radiotoxic atoms. So these are normal atoms, the fission products. The enriched starting fuel comes from there. The fuel replenishment comes from there for centuries. The fuel cycling methodologies we have to build on site. Pyroprocessing is what I recommend. It's economical, efficient, and has minimal working waste. You say, do we still need a deep geological repository for it? I think the waste is too small to do that. You might drill a borehole and put it that way. Fast spectrum modular reactors you can buy. They're available from 3 megawatts to 300 megawatts. And NB Power in New Brunswick is actually looking at this one, which is 100 megawatts. So in Canada, we're going in that direction. Time frame, as I indicated, it takes about a few decades to acquire the fuel for these reactors. And then after that, you've got the uranium left, which is replenishment of fuel for centuries of nuclear energy. I think that is my story, and I would say that it would give us long-term energy security in Canada and energy sovereignty and independence. We won't have to worry about Putin giving us enriched fuel, nor do we have to worry about a potential other President Trump that puts an embargo on aluminum and steel. Well, U-235 is much more important than those, so he would certainly put an embargo on that. And remember, it's carbon-free energy. Nuclear energy is carbon-free energy. So it's something that we should stay in and go into in a bigger way. And so this is my final slide. Remember, the next time you have a cup of coffee, that lump of sugar in terms of used fuel is worth $21,000. Thank you very much. Now, I'd be happy to take questions, if I may.
What happens to the fuel when it's finished in the SMR?
Oh, okay. The SMR is basically, sorry, I can speak into this thing. The SMR.
Should we get him to ask the question?
I'm sorry. Turn the fuel down by 15%. So instead of topping it up and having the same number of reactors, you can take that fuel, which is 85%, and now put it into 85% of all the reactors you have. So if you had 100 reactors before, you now have 85 reactors. You do it again, you have another 15 that are less, and so forth. So you can work your way down to one reactor that way. And basically, then you've got a lump of radioactive transuranics, which I suggest you carve up into little pieces and send them out to the universities of the world, because it's going to be the last such fuel ever. It's okay. Don't worry. I will answer any question. Yes.
Yes, thank you. Thank you for your presentation. Again, I'm Norm Bush. I do have a number of questions, I guess, with respect to the technologies and the applications of the technologies. With these fast spectrum reactors, and again with the small modular reactors, I know they're being looked at and developed, at least in the design stage, by a number of companies. Are there any actually licensed and up and running in Canada?
In Canada, no. Uh, we're just looking at those because we decided to go into CANDU reactors which use natural uranium, whereas any of these reactors require enriched fissile material for them to operate. This is why we didn't go into light water-cooled reactors either way back when, because they also require enriched fuel. And so, essentially, I would say that the Canadian involvement has been that Canadians actually developed that first reactor that first created electricity from uranium, which was the EBR-2. That was Walter Zinn, who was born in Kitchener. And the recycling process, the pyroprocessing, was developed by another Canadian from Aylsham, Saskatchewan, Chuck Till. So we've had Canadian involvement in this. We just didn't bring the technology home yet. So it's about time that we repatriated it, I think.
Yeah, I understand that the Canadian decision in the past not to get into enrichment facilities for a variety of reasons, political, military, and others, but it seems to me that what we're talking about here is a pretty major shift in energy production, potentially for the North, which could be decades in the making if we're looking at bringing small and large nuclear reactors up here and fuel processing facilities. It seems to me we would still be looking at the transportation of spent nuclear fuel, processing it up here instead of storing it. And I'm just not sure of where we are technologically with the development of these reactors, and also from a licensing perspective and economically what the total balance looks like. So it just looks to me like there's a lot more work that needs to take place in terms of the design, the building, the licensing, the functioning of it, and also the economics. You know, there's one thing about the economics around the fuel, but I've got questions around the whole economics of building and operating the facilities, the nuclear power plants associated with using that fuel, but also the spent fuel processing facilities, and what does all that look like at the end of the day. And it seems like there's a lot more work that needs to go into it before we have the kind of answers that we need to know whether long-term it makes sense for Northwestern Ontario to get into being supplied by nuclear reactors and also having a spent fuel processing facility up here versus potentially a DGR. Those are just my thoughts.
Let me give you an example. The reactor that was built, the EBR-2, it ran from 1964 to 1994 already. So basically the development of the technology is done. All we have to do is copy and do it if we want to build our own. You can buy. The other thing in terms of putting things in isolated places, Pickering was farmers' fields when OPG first built their reactor. Pickering now, after 50 years, is a bustling town of over 100,000 people. So basically, if you build it, they will come. I would not sell any region short in terms of tackling a development like this and making it work. In terms of work to be done, well, that's good. That's jobs. Well, you can capture, oh, there's another one here.
Hi there. I understand that the nuclear lab in Pinawa and the waste that was produced there is apparently leaking into the environment. I wonder if you could speak to that.
Well, I mean, this is why you know, I told you that the measurement that they made in Pinawa of water flow in that pluton, which they thought was dry stuff, that's why they picked the plutons, was as fast as that. I was flabbergasted when I found that it would go 25 meters in a week. So, yeah, I wouldn't be surprised if you say, well, but in Pinawa, in the Pluton, they wouldn't have radioactive stuff. So is this from the reactor in Pinawa itself? Yeah. No, basically, the thing is, if you store the radioactive waste, then I would say, with time, eventually something's going to happen. But what I'm suggesting here is that you use it, you stick it back into the reactor. And then what comes out in the process is short-term radioactive stuff. So even if that leaks, it'll decay away within the order of decades.
The Pluton's hydraulic conductivity is much greater than you originally thought. And because of that, the nuclear repository that is proposed for the Ignace area is in the same boat, that the hydraulic conductivity could be considerably higher than calculated.
Well, it seems to me you have to measure it because the material doesn't go through solid rock. It goes through fissures. It goes through cracks, and if you have enough cracks that are continuous enough, then it'll move under a bit of pressure. So I would say you have to await the results of the borehole experiments that they did up there. They've I think, drilled the boreholes, but I haven't seen any results in terms of conductivity measurements.
Okay, and just one supplemental. I understand from word of mouth that the boreholes on this site are full of water.
I would say any hole that you dig anywhere will fill up with water. I mean, you've probably noticed that in your backyard as well. I don't know where the water comes from, so I have no idea other than that they said they've drilled the boreholes and they've got core samples and so forth. I don't know what any answers are.
Yeah, it's Joe Howe here. Thanks, Peter. That was really good. I was very intrigued. I'm a bit of a nuclear junkie, so I love that stuff. Certainly at NWM, we're always looking at that. Part of our APM process is to look at recycling, and we put a report every year on recycling. So stuff like what Peter has talked about, we're looking at continuously as part of our process. With respect to the borehole, though, you're right. One of the measurements that we do on the rock is something called hydroconductivity, the K value as that. So we have put out a statement of confidence with respect to the rock and the analysis thus far that we've done on the Pluton, the Revel. We're getting numbers of 10 to the minus 12 at this point in time for the movement through the rock in areas which we're looking at this point in time. And you're right, water flows through fractures. And that's exactly the nature of the work we're trying to do. We're trying to prove and show and demonstrate that the fracture network is such that it's disconnected from the surface. That's the whole idea behind this, the research. And if we can't prove that, it can't be done safely. So definitely we're trying to demonstrate that. The other way in which we demonstrate, that the rock is separated is we actually look at the age of the water in the deep sort of zone there. And the numbers right now are showing that the age of rocks are greater than 1 million years. The age of the water is greater than 1 million years. So that's one other additional piece of evidence that we're looking at when it comes to the rock.
We have one final question, and then we are going to have to move on to our next presenter, but I'll pass the mic.
Actually, mine's not a question. It's on the previous set of questions with respect to small modular reactors. So For those who I haven't met yet today, my name is Nancy Greencourt, and I'm the Director of the Waste and Decommissioning Division at the Canadian Nuclear Safety Commission. And the question was with respect to the license application for small modular reactors, or SMRs. At this time, the CNSC has not granted approval to operate a small modular reactor. But if, in cognizant of time, and it's outside the scope, if anybody would like to have some questions about the process for license applications and the status of small modular reactors, we'd be happy to discuss it at the break.
Thank you.
Right. Thank you, Nancy. Thank you, Joe, and thank you, Peter, for your presentation.